Now we'll finally expand our discussion of heat. We will identify and describe thermal energy flow. We'll define heat capacity and relate temperature change to our heat capacity, both conceptually and mathematically. Heat is an exchange of thermal energy. It is a transfer of energy, not the energy itself. Temperature is a direct measure of this thermal energy. Therefore, a temperature change will measure our heat change. Whenever there is a difference in temperature, heat is going to flow from the high temperature to the low temperature until that temperature is the same. We call this temperature being the same as thermal equilibrium. We can look at an example of this with our woman holding a coffee cup. There are several different places that the temperature change makes heat flow. Heat flows from the coffee cups into the woman's hands. This is why you feel your hands warm up when you hold coffee. But heat is also flowing from the woman into the environment because she is warmer than the environment. Heat is also flowing from the coffee cup into the environment. Anywhere where there is a difference in temperature, there is heat flow. So we already said this, but one more time, temperature is proportional to the heat absorbed. But that doesn't necessarily mean that it is the same for all species. We need a measure called heat capacity. This is the amount of heat that a system must absorb to undergo a specified change in temperature. Typically, this is described as 1 degree Celsius. So the amount of change that you have to put, or the amount of heat that you have to put into, let's say, water to make it change 1 degree. Water has a very high specific heat capacity. This is why some place like Newport Beach is nice and comfortable at 80 degrees, while some place like Riverside is very warm at 115. The heat goes into heating the water. Something like iron has a lower heat capacity. Only a small amount of heat is needed to be added, and it will raise the temperature very quickly. We have several ways of reporting heat capacity. You can just talk about heat capacity as the capacity of a whole entity. Typically, we talk about this in calorimetry as the heat capacity of the entire calorimeter. More often, we're talking about it in terms of one species. And it's different depending on if it's a gram or 20 grams or 50 grams. And we can't tabulate that for every single value, and so we do it per gram. Where our molar heat capacity is per mole. Now, we have an equation for this, and there's several related equations just based on the units. The most common version of the equation is Q equals mc delta T, or Q equals mcat is the way to remember it. This is in relationship to the specific heat capacity, or the heat capacity per gram. And so you multiply your heat capacity by your mass and your change in temperature. That gives us our overall Q. But there are two very related equations. Really, you should just remember this first one, and then know that it can be changed based on the units. If you are instead given a molar heat capacity, so you're given the heat capacity per mole, you can multiply by mole instead to get the heat, just following the units. And lastly, it's less common. It will come up in calorimetry for sure, but it's Q equals C delta T, no M. And that comes into play when you're given the heat capacity of the entire sample, or the entire entity, or the entire object. There's no moles or mass to be added, so you just multiply by your temperature. Now, remember, you're not memorizing all of these equations separately. I would stick with memorizing Q equals mc delta T, and then just know that that M may or may not be there. And it may mean mass or it may mean moles, just depending on what your C is given to you in units. So our specific heat capacity is in joules per gram degree Celsius. There's a grams in the denominator, so we would fill in grams into our equation. We also have our molar heat capacity, which would just be listed in joules per mole degree Celsius. And here we can still think of it as Q equals mc delta T. It's just our M would be moles instead of mass. And I give you a list of them. This is obviously not an all-inclusive list. You'll be given the heat capacities if you need them. For homework, it's in the back of your book. Now let's do an example using this. That's the simplest way to explain how the problems work. We have a 25-gram chunk of metal. We don't know what the metal is at 27 degrees Celsius, and it's put into a heated container. We can measure how much heat it absorbs. This is probably done by using a thermometer, and we'll talk about how that's done in a later problem. But for right now, I just tell you that it's 2.35 kilojoules and that it becomes 427 degrees Celsius. What is the species? So we have our Q equals mc delta T. Now this time we're solving for C. And we're solving for C because it will act as an identifier for what the material is. You can actually use this to maybe tell the difference between gold and fool's gold because they have a different specific heat. In our case, we're just going to identify it and assume it's one of these ones on the table. So we'll solve for C. I rearranged my equation first, just out of preference. You could obviously fill in first if you'd like to. Be very careful with your temperature that it's final minus initial. Otherwise, your sign will be a little wonky. So we fill in our values. Notice what I filled in for Q. So compare it to what I put in the question. 2.35 kilojoules in the question. And when I fill it into the equation, I do it in joules. And that's because it's tabulated in joules. Our C is tabulated in joules. And so it seemed proper to put it in the units that we're going to be comparing it to. When we get all done, we get our value. It's 0.235. So we walk over to the table. We look through the table. We find a value that's 0.235 or very close, because maybe it's not perfect, but it's close. And we see that, yes, there is one. And that's silver. And so we know our species is very likely silver. So let's talk a bit more about thermal energy transfer. We already said that thermal energy transfer occurs when there's a difference in temperature, and that the energy flows from high to low temperature. That's all review. We also know that because of the first law, energy change of the system must be the same magnitude, but opposite in sign, as the surroundings. Or in other words, the energy flows to the system from the surroundings, and it must be the same amount. The direction is just different. So we can write that in terms of an equation. We can say Q is equal to negative Q of the surroundings. We call that equal in magnitude, opposite in sign. Same amount, just different signs. And we know in equation form that Q is equal to mc delta T, right? That's our thermal energy transfer. So now we're going to combine this together to come up with another, it's not really another equation, but a way of using the equations that's really useful to us. So we'll fill this into both, because the Q of the system and the Q of the surroundings will both be Q equals mc delta T. They'll simply have different C's and different masses and different temperature changes. So when we do this, we get Q is equal to mct of the system is equal to Q is equal to mct of the surroundings. And we can use this to solve other types of problems that are a little bit more authentic than the previous one that we just did. So now we have a problem very, very similar to our previous one. I tried to set it up as close as possible, except now that we aren't given the heat transferred. However, we do know that the heat is absorbed by the water, and that this must be the same heat as let off by the metal, just opposite in sign. So we have our 25-gram chunk of metal. This time our chunk of metal is very warm and is put into an insulated container with a certain amount of water. The water was initially at 298. And when the sample comes to equilibrium, our sample has cooled down to 301. What is the species? Now, I tell you to assume that water's density is 1 gram per mil. That's usually given as well. So first off, we're going to start with our Q equals Q form of this equation. Our mc delta T is equal to negative mc delta T. don't forget that negative sign or things will go wrong. You don't have to worry about whether the negative goes in front of the surroundings or the systems. That won't matter to your problem at all. Just make sure that it's on one side. And then be very careful as you go to put in each of your numbers that you keep your numbers straight. So when we start with our system, that's our chunk of metal. We have 25 grams. We don't know what the C is for our system. That's what we're trying to find so that we can identify the species, just like we did in the last problem. We do know our two temperatures, though. We know that it started at 601 and that it ended at 301. Moving to our surroundings, we know that our initial temperature of our surroundings, our water, was 301 or was 298, and that it was raised up to 301.4. So we know that temperature change. We can look up our C for water. C for water doesn't change, so we can always go look that up, and it's 4.18. And we know our mass of water because it's 205 mils, which means that it's 205 grams. For the sake of room here, I didn't include my units. It's probably a good idea to do so when you aren't cramped for space. So now finally, we solve for our C. We rearrange all of our numbers. I'll give you a second to look at that. And then we get our final value. With this final value, we can do the exact same thing that we did with our previous problem. We can go look at our table, find our 0.385. In this case, there isn't an exact match, but there's one that's very, very close. It's 0.385. So we can look at that one and say, oh, this one's going to be copper. So very similar problem. You should kind of look at them side by side now that you've seen them both. In the first case, I gave you the heat. In the second case, we calculated the heat, right? That's what we did when we found MCT of our water. We were calculating the heat absorbed. And then we used this to solve for our C. So now our quick review. Heat is our exchange of thermal energy between a system and the surroundings. It is related to the transfer, not the energy itself. Temperature is our measure of this. It gives us a measure of our thermal energy in our system. This thermal energy exchange, this heat, is going to occur whenever there is a difference in temperature. It's going to flow from a high to a low temperature. And this continues until thermal equilibrium is reached, or in other words, until something is the same temperature. Using Q equals MC delta T, either in its individual form or when we have them both together, can be used to calculate delta T, final temperature, initial temperature, mass, heat, or C, given that you're given the other ones in the problem.